Experts believe that space exploration will be forever divided into two eras, before and after the James Webb Space Telescope. This isn't surprising, considering the telescope's groundbreaking discoveries have already exposed major gaps in our current cosmic models. Webb has detected numerous structures that, according to our existing understanding, shouldn't exist in their observed forms. This is particularly evident in objects that emerged shortly after the so-called Dark Age, appearing far too large and massive for such an early stage of cosmic evolution. As a result, scientists are increasingly recognizing that our traditional theories about the early universe are incomplete. There is still much to uncover before we can truly comprehend this mysterious period. When we gaze at the countless stars illuminating our night sky, it's astonishing to think that the universe was once shrouded in total darkness. The universe has undergone remarkable transformation since its birth 13.8 billion years ago. In its first 380,000 years, it existed as a scorching, dense ionized plasma. However, as it cooled, protons and electrons combined to form neutral hydrogen atoms. This ushered in the so-called Dark Age, a time when no stars or galaxies had formed, leaving the cosmos as a vast, transparent expanse filled with a dense fog of hydrogen gas. The universe's return to illumination was driven by the first stars and galaxies, which formed around 100 million years later. Their intense ultraviolet radiation gradually reionized the cosmic gas, freeing electrons from protons and transforming the universe. Scientists call this pivotal era the cosmic twilight. While much about this period remains a mystery, the James Webb Space Telescope has already reshaped our understanding of how it unfolded. Engineered for infrared astronomy, this $10 billion masterpiece allows us to gaze deeper into the cosmos than ever before, revealing the earliest structures that emerged after the Dark Age. Its discoveries have been nothing short of groundbreaking. If you are even a little bit interested in the subject, you will have heard that Webb detected 6 early galaxies as early as 2023, which embody nothing less than an astronomical impossibility. More specifically, this refers to the fact that the structures already existed 500 to 700 million years after the Big Bang, and despite all this, they were already as massive as our Milky Way is today. Accordingly, all 6 galactic premature babies contain more than 10 and, in one case, even more than 100 billion solar masses of stars. To explain the existence of such massive galaxies at this early stage, either the density of matter in the young cosmos would have to be 2 to 5 times greater than predicted by the standard cosmological model, or the galaxies would have to have grown in a way that is completely unknown to us. In view of this, it's probably not particularly surprising that the galactic mysteries henceforth became known as universe breakers. But in truth, this was only the prelude to a series of no less confusing Webb discoveries that have since given scientists a severe headache. On one side, we have the galaxy JWST, GS-Z140, which formed just 290 million years after the Big Bang. Strikingly, it appears far too massive and densely packed with stars for such an early stage in cosmic history. This raises a fundamental question: how could a galaxy amass several hundred million solar masses of stars in less than 300 million years? Before the James Webb Space Telescope provided an unprecedented glimpse into the early universe, astronomers believed that only small, low-mass galaxies populated this ancient cosmic era. This idea was rooted in well-established theoretical models, which suggested that, so soon after the Big Bang, the universe simply wouldn't have accumulated enough normal matter to form large galaxies or sustain rapid star formation. However, the discoveries made by JWST have upended these assumptions. Not only has it revealed a surprising abundance of massive galaxies from this period, but some of these cosmic giants, nicknamed red monsters due to their extreme brightness in infrared light, are so unexpectedly large and mature that they challenge our very understanding of how galaxies evolved in the universe's infancy. These findings suggest that either our models of galaxy formation need significant revision or that unknown astrophysical processes were at play in the early cosmos. Is the standard model of cosmology wrong? In view of the constant stream of new surprises that the universe now reveals with increasing regularity, a fundamental question arises. If so many structures are found out there that blatantly contradict the standard model of cosmology, could it be that this model is simply wrong? Now, to find out for sure, a research team led by Mangan Xia of the University of Geneva has set out to systematically search for the early outlier galaxies once again. In the course of this, the scientists evaluated the data collected by Webb's near-infrared spectrometer, NIRCam, and in it, they actually discovered 36 more massive, dust-enveloped galaxies that existed around 1 billion years after the Big Bang. Ultimately, Webb's high-resolution spectra penetrated the dust veils that made the galaxies practically invisible in the optical spectrum, whereupon the team set about analyzing the corresponding stellar mass and its relationship to normal and dark matter. Amid the vast and seemingly endless galactic expanse, astronomers identified three extraordinary objects that stood out due to their immense size and deep crimson hue. These enigmatic structures, unlike anything seen before, quickly earned the nickname Red Monsters. What makes them even more remarkable is their sheer scale. Each one rivals the Milky Way in mass yet exhibits an unusually high rate of star formation. To put this into perspective, these cosmic giants are birthing stars at an astonishing rate of 795 to 1,300 solar masses per year, a phenomenon that far surpasses typical expectations for galaxies of their size. This unprecedented level of activity has left scientists both fascinated and perplexed, adding yet another layer of mystery to these cosmic behemoths. The already existing mystery of producing so many celestial bodies in such a short time suggests that the three red monsters have to convert much more gas into stars than usual. To achieve this, researchers state that their so-called conversion rate is 2 to 3 times higher than what would typically be expected for the most efficient star formation in younger galaxies. This is because such galactic youngsters can only use around 20% of the available gas for star formation. However, the red monsters have apparently managed to circumvent the numerous processes that normally limit the efficiency of star formation. What does this discovery mean on a larger scale? For the standard model of cosmology, this finding brings encouraging news. There's no longer a need to assume an extraordinarily high matter density in the early universe to explain the rapid formation of massive galaxies. However, the existence of these enigmatic red monsters challenges our understanding of how galaxies evolve over time. Their presence suggests that star formation and galaxy growth in the distant past followed a very different path compared to what we observe today. According to Shia and her team, this discovery provides compelling evidence that the early universe was 2 to 3 times more efficient at assembling galaxies than previously thought. Yet, the mechanisms driving this accelerated formation remain an open question. Were there unknown physical processes at play? Did dark matter or exotic interactions play a role? What is undeniable, though, is that these colossal red galaxies mark a turning point in our comprehension of the cosmos. They raise profound questions about the universe's history and challenge long-standing models of galaxy formation. As astronomers work to unravel this mystery, one thing is certain: the past and present of our universe are proving to be even more complex and fascinating than we ever imagined. Observations of the universe suggest that it is expanding at an unexpectedly rapid pace. As we know, the universe has been expanding continuously since the Big Bang, with its rate of expansion accelerating over time. To explain this phenomenon, scientists have proposed the existence of dark energy, a mysterious force believed to counteract gravity, though very little is actually understood about it. However, the precise rate of the universe's expansion remains a topic of intense debate. While the Hubble constant, a fundamental cosmological value, is meant to define this rate, a major discrepancy exists. According to the Standard Model, the Hubble constant should be around 67 km per second per megaparsec. For reference, a megaparsec is approximately 3.26 million light-years, meaning galaxies should be receding from each other at an increasing speed of 67 km per second for every 3.26 million light-years. However, real-world astronomical observations, using supernovae, gravitational lensing, and variable stars, indicate a different value: 73 km per second per megaparsec. To put this mind-boggling figure into perspective, it translates to a staggering 20,000 km per hour for every megaparsec, a scale so immense that it challenges our very perception of cosmic motion. But what could be responsible for such a significant discrepancy in the universe's expansion rate? Could it simply be due to measurement errors, or is there something far more profound at play? That's precisely what Nobel laureate Adam Rees and his team at Johns Hopkins University in Baltimore set out to explore. To resolve the ongoing debate, they turned to the powerful James Webb Space Telescope, using its advanced infrared capabilities to reassess crucial data previously obtained by the Hubble Space Telescope. The goal? To determine whether past measurements contained inaccuracies or if the cosmos itself was defying expectations. After analyzing Webb's most comprehensive dataset to date, the team arrived at a stunning conclusion: the universe is not behaving as our best theoretical models predict. Their findings once again pointed to a Hubble constant of 72.6 km per second per megaparsec, reinforcing the persistent tension between measurements of the present-day universe and predictions derived from the early cosmos. According to Rees, this result strongly implies that our current understanding of fundamental physics remains incomplete. Could an unknown factor have given the infant universe an unexpected boost following the Big Bang? Or does dark energy possess properties that scientists have yet to uncover? Perhaps the answer lies in a new form of exotic particles, undiscovered elements of reality that could reshape our entire conception of cosmic evolution. One thing is clear, the mystery deepens, and the universe continues to surprise us.